Hi, and welcome to Chapter 3, Section 2. Today we're talking about Rolle's theorem and the mean value theorem. So first I want to lead off with both of these theorems are actually really similar to each other. For both of them, we're talking about some sort of function, a graph of some sort, and we're looking specifically at an interval from a to b, so an x value of a to an x value of b. An A and B can be anywhere on the graph. I just kind of chose these two random points. But basically, we're looking at where the graph crosses, what the point is when it crosses A and when it crosses B. And we're looking for the slope between those 2 points, basically. So, if we were to draw a line here between connecting my points from A to B, then the slope at that line of that line, they're basically somewhere else within the interval from A to B, there's going to be a point where it has the same slope. The tangent line of that point has the same slope as the line that's drawn right now. So like right here at point, we'll call it x equals c. If we drew the tangent line of that point, it would have a slope that's pretty much the same as the slope between A and B. And so basically, this is the mean value theorem. It's saying is that that point, that x equals c, exists. We want to be able to find it, but that's all it's saying. So between any 2 points, whatever the slope is between those 2 points, there has to be a point somewhere within that interval that has the same slope. That's all it's saying. So Rolle's theorem is pretty much the same thing, except that the points for A and B, they have to have the same y value, meaning the slope between them is 0. So here in my new graph, I've just chosen different positions for A and B. So again, A and B could be any number, it's whatever's given to you. But here, where the points for A and B are, they have the same y value, so like you see, same height. So if I were to draw a line between those 2 points, if they have the, if they have the same y value, that means the slope of that line would have to be 0, because it's perfectly flat. So, sorry, got a little spooked there because the door closed by itself. It's because my window's open. But yeah, anyways, so the line between those 2 points is perfectly flat, so it has a slope of 0. So Rolle's theorem says that there's some other point x equals c that has a slope of 0 for its tangent line. And so in our graph, if we were to look for this point, we would see like right here, we could call that c because its tangent line would be like that, which is, again, perfectly flat, slope of 0, which matches the slope between A and B. So again, for both of these theorems, the mean value theorem and Rolle's theorem, they're basically saying the same thing. It's just Rolle's theorem is a little bit more specific. They just want a perfectly flat slope of 0. Whereas the mean value theorem, we don't care what the actual slope between A and B is. We're just saying somewhere else within that interval, there's going to be some other point that has the same slope. Okay, so far I've been talking about mean value theorem and Rolle's theorem in like very, non-mathy terms right now, because all we've talked about is like slope. So how does this deal with our derivatives? Well, if you remember, slope and derivatives is pretty much the same thing. When you find a derivative, it really gives you the slope of a tangent line at a certain point. So when I say the slope is 0, where at x equals 0, or at x equals c, the slope has to be 0, that just means when I find the derivative of my function f, then when I plug in whatever point c, then it has to have, the derivative has to equal 0. So same thing with the mean value theorem. Whatever the slope is between A and B, the derivative has to be set equal to that in order to figure out what number is c. I also wanted to point out 2 rules that has to happen before you can use the mean value theorem and Rolle's theorem. Those 2 rules are that the function f of x must be continuous on that interval from a to b. So whatever the given interval is, it has to be continuous there. So if we have any like holes, vertical asymptotes, anything like that, then we wouldn't be able to use Rolle's theorem or the mean value theorem. The other rule is that f of x must be differentiable on the interval from a to b. So that means no sharp turns, no vertical tangent lines, the limit has to exist, all that good stuff that we've talked about before. All right, so let's do an example together. Okay, we're going to use Rolle's theorem to find all values of c in the interval from -3 to 3, such that f prime of c, so the derivative of c, equals 0 if f of x equals x to the fourth minus 8x squared plus 7. So here, since we're using Rolle's theorem, first we have to actually verify. We have to verify that our two rules work, that f is continuous and differentiable on the interval from -3 to 3. So our function is x to the fourth minus 8x squared plus 7. It's just a polynomial function. There's no discontinuities or anything like that. We can definitely find the derivative of this function easily. So continuous and differentiable. Okay, the other thing I need to check, since we're using Rolle's theorem, is that the y values when x equals -3 and the y value when x equals 3 are both the same, because I need to make sure that the slope between these two endpoints are actually going to be 0. So when I plug in -3 and 3 into my f of x, I end up with y values of 16 for both of them, which means the slope between these 2 points then would be 0. Okay, so Rolle's theorem works. Let's actually find those values of c then, where the slope is actually equal to 0 for those x values of c. Okay, so if our function is x to the fourth minus 8x squared plus 7, in order for the slope to equal 0, we have to find the derivative and then set that equal to 0. So the derivative of f of x using the power rule would be 4x cubed minus 16x. Okay, then from there, we're looking for all the x values where this derivative equals 0. So I'm going to set my derivative equal to 0 and then solve for x. Once I solve for x, that'll give me the values of c. I'm going to solve for x here by factoring. So I can factor out a 4x, and that'll leave me with x squared minus 4. And I can factor that even more with x plus 2 and x minus 2. Which means I'm going to end up with solutions of 0, -2, and 2 when I set each of my parentheses equal to 0. Okay, so that means all three of these values count as values of c, because all three are in between the interval from -3 to 3, so all of them work. And all three of these values are when, if I were to plug this into the derivative, it would give me a derivative equal to 0. So those are my values of c. All right, my next example, I'm going to find the x-intercepts of f of x equals x squared minus 3x plus 2, and then show that f prime of x equals 0 at some point between the x-intercepts. So here, it's a little bit different because they're asking us to find x-intercepts first. So for this one, because we're looking for x-intercepts, they haven't given us endpoints at all. So they didn't tell us what interval to look for them. But if we're trying to show that f prime of x equals 0, this gives me a pretty good clue that this is going to be Rolle's theorem, because Rolle's theorem is the one where we set the derivative equal to 0. So another thing is with x-intercepts are where the graph crosses the x-axis. So when they cross the x-axis, they should have the same y values, meaning whatever the x-intercepts are, those 2 points would be my endpoints of that interval because it's where it has the same y values. So the slope between two x-intercepts has to be 0 as well. So we're basically, for this problem, looking for our own 2 endpoints for our interval, and then showing where the other point is, the x equals c, that has the slope of 0 as well. So let's start off by finding our x-intercepts. X-intercepts are found when y equals 0. So I'm going to set my equation of f of x equals x squared minus 3x plus 2 equal to 0 and solve for x. I'm going to solve by factoring here. So I think x squared minus 3x plus 2 factors into x minus 2, x minus 1. So that would give me solutions of 2 and 1, which means if I were to graph this out, this graph would cross the x-axis at x equals 1 and x equals 2. So those are my endpoints. We're basically saying, look at the interval from 1 to 2. And then we want to find an x value between 1 and 2, so between that interval, where it also has a derivative of 0. So to find a derivative of 0, let's set our equation, find the derivative of it, and then set it equal to 0. So the derivative of f of x would be 2x minus 3, We're going to set this equal to 0 and solve for x. So adding 3 to both sides and then dividing by 2, x equals 3 over 2. So 3 over 2 is like what, 1.5? 1.5 is a number that's between 1 and 2. So we want to make sure whatever x value we solve for, it actually falls between the interval that we want. So this does work. And so that's our like c value that we've been looking for. So x equals 3 over 2 is where the derivative would equal 0. We did it. All right, this next example, we're going to use the mean value theorem this time. So we're going to use the mean value theorem to find values of c such that f prime of c equals, and then there's this weird formula. This is just the slope formula. Remember, slope is y2 minus y1 over x1, x2 minus x1. So if a and b are our like x values for x1 and x2, then f of b, f of a just means like when you plug in a and b into your equation, what y values would you get? So here's our y2 minus y1 over x2 minus x1. So we're just finding the slope between the 2 points of a and b. Here's our equation on the interval from -2 to 5. So -2 would be our a technically, 5 would be our b. So just like before when we used Rolle's theorem, we had to verify that our function was differentiable, that it was continuous, and that we had the correct slope. So when we look at our function, x cubed minus 8x squared, this is a polynomial function again, so this is going to be continuous, differentiable everywhere. And then let's actually find the slope between the 2 points, -2 and 5, so that we know what slope we're trying to set, or to find c where it has that slope. So to find the slope, we know our x values are -2 and 5, so we would need to find our y values. So I'm going to plug into the original equation so that I can find the y values for each. Okay, so when I plugged in x equals -2, I got -40, so that's our y1. For x equals 5, I got -75, so that's our y2. So that means our slope, when we do our f of b minus f of a over b minus a, is going to give me 5 minus a -2. Oh. -75 minus a -40 over 5 minus the -2. Okay, and that'll end up with a slope of -5. Okay, so we know what the slope is now between a and b, like our two endpoints from -2 to 5. So now we just have to figure out where the derivative is also equal to -5. So my derivative, f prime of x, is going to be 3x squared minus 16x. So finding the derivative of f of x. And then I'm going to set that equal to the slope that I want it to be, which is -5. And then we're going to solve for x. So because I have an equation with an x squared in it, I'm going to set it equal to 0 so that I can actually solve it. And I'm going to solve by factoring here. I think it factors into 3x minus 1 and x minus 5. So that means I'm going to get x values of 1/3 and 5. Okay, so now that I have my x values, it's kind of like I've just solved for c, except I need to make sure that whatever answers I get are actually within the interval that I asked for, so the -2. So the 1/3 is between -2 and 5. The 5 is also between -2 and 5 because even though 5 is the endpoint, I have the square bracket, meaning we're including the 5. So both of these values work. If my interval had parentheses instead of the square brackets, that would mean we would not include the -2 and the 5. In that case, the 5 wouldn't be included as our answer. But here, because we have the square brackets, we are including the 5. All right, and that's all you need for this section. Thanks for watching. Bye.